My name is Yu Weifang, a PhD student from Institute of Information Engineering Chinese Academy of Sciences. My current research interests include cloud security and IoT security.
Today we bring you a presentation entitled IoT Manufacturers New Nightmare, Design Flaws and Deployment Chaos in Cloud-Based IoT Access Control Policies. This is joint work by 6 authors, including Yi Wei, me, and Yan Jia, Bingyuan, Qixu Liu, and Lu Yuxing. Yi Wei and I will be presenting. And this work was also published on CSS 2022. And the name of the paper is P-Verify, Understanding and Mitigating Security Risks in Cloud-Based IoT Access Policies. Yi Wei will bring the first part.
First of all, we get started with the background knowledge. The Internet of Things Cloud is one of the key pillars of the foundation upon which a modern IoT system rests. Newer IoT devices and their manufacturers take advantage of the much less studied third-party platform as a service, also named PaaS, infrastructure as a service, also named IaaS, IoT Cloud Service, such as AWS IoT Core, Azure IoT Hub, and Tuya IoT Cloud, which offload much of the security responsibilities and deployment burden to the public cloud providers. Such IoT clouds just manage hundreds of millions of IoT devices and provide device manufacturers with reliable and usable tools for secure IoT developments. In general, the convenience of accessing resources in the cloud is made secure by developers with specified access control policies. A cloud-based access policy is an expressive specification of what resources can be accessed using what actions, by whom, and under what conditions. Cloud providers such as AWS and others generally define a policy language that lets developers govern access to resources in the cloud. A cloud-based IoT access policy, taking AWS IoT as an example, inherits the syntax of the service-agnostic AWS IAM policies and is an extension of IAM policy in the IoT context. An IoT policy specifies which users or clients can access which IoT devices or resources under what constraints, and specify action or resources types in the IoT context, such as publishing a MQTT message. To better understand the IoT context of the modern IoT cloud, we now introduce the MQTT protocol here. MQTT is the short name of Message Queuing Telemetry Transport Protocol. MQTT is arguably the most popular messaging protocol in the cloud-based IoT communication. MQTT leverages a classical publish-subscribe pattern. The client publishes a message to a named topic hosted by the server, which then relays the message to other clients that subscribe to the topic. The topic is named similarly to a file path with multiple levels separated by slash, such as /device ID /status. The above figure shows an MQTT topic. The green words are the content of topic levels, and the red slashes are topic level separators. A classic usage is to use different levels of the topic to delimit the scope. For example, home, root, or device. Let's see the figure. First of all, the client connects with the cloud server. An IoT device subscribes to its unique topic by sending a subscribe message to the server. The server maintains the subscription status. The user's app can command the device by publishing messages to the topic that the device subscribes to. Also, the device can publish messages to the topic that the user app subscribes to. Once the subscribe-publish channel is established, the MQTT broker, or specifically say the MQTT topic, is working as a communication channel, and users and devices can exchange messages through this channel lightweightly. Clients can use MQTT wildcard plus or hash to subscribe to multiple topics. Plus is a single-level wildcard that represents one topic level and must be placed alone as one level. And hash is a multiple-level wildcard, and it must be placed as the last character, also as the last level. Now we've introduced the basic building blocks of cloud-based IoT context. We note that the MQTT approach to communication is lightweight but more complex than the traditional request-response model of communication. Then this communication model with cloud-based IoT context access control can bring developers huge error spaces. Let's take a look at the flaws we found. To understand the error space and security challenges in cloud-based IoT development, we studied the practices of 36 mainstream IoT devices manufacturers and 310 GitHub projects. Note that the error space means the design of AWS IoT Core provides spaces for vendors to make mistakes. Not AWS IoT Core itself leads to the error or flaws. The first error space we want to share is a design error space, semantic gap in IoT access policies. Let's take Hibakura as an example, and it is a Japan's well-known online consultation platform. In its design, any user or client only needs to know the communication channel with the doctor to communicate with each other using the MQTT protocol supported by AWS IoT. For example, users can subscribe to its XMD/session/session ID to receive the message sent from their doctor and publish it to their own XMD/session/session ID to send a message. With this design, the MQTT topic works as a separate channel. However, as we mentioned, MQTT supports wildcards. Once the wildcard can be used, the session ID in the MQTT topic loses its secrecy. Hibakura is also aware of this problem, and they have rejected the XMD/session/hash in their IoT policy. However, as the wildcard hash can match multiple levels, another topic such as XMD/hash can also access the resource XMD/session/session ID. So, an unauthenticated attacker can monitor all the messages on Hibakura's AWS IoT. Another vendor that made these mistakes is Govi. Similar to Hibakura, Govi uses LWT/ as a notification channel for devices disconnections, and they taking advantages of another feature of the MQTT protocol, which is called the last will message. Govi has even stricter restrictions on wildcard than Hibakura, which, according to our backward speculation, restricts star plus and star hash. However, it does not restrict topics such as +/. So we can subscribe to LWT/ with +/. Now let's see this demo video. The attacker can subscribe to the topic XMD/session/hash to see the messages because of the Hibakura's policy. But he can use the topic XMD/hash to bypass the restrictions, so he can monitor others' message. And he can also subscribe to specific private topics.
In order to understand the error space, we have to introduce the overall architecture of the cloud-based IoT platform, focusing here on AWS IoT, Cognito and AWS IAM. AWS IAM is the centralized permission management service that allows clear delineation and permissions between services. roles and users with the help of IAM policy. AWS Cognito is a user and identity management service in IoT context. Developers or vendors can leverage the service to add user management to their IoT service. Let's see this figure. This is a typical structure of an IoT app based on AWS IoT and AWS services. Users log in and obtain identity from AWS Cognito service, and the devices directly interact with AWS IoT via device certificates. Users can control or monitor devices under asset control from AWS IAM and AWS IoT. But when we dive deeper into understanding the principles of this architecture, we found confusingly complex interaction principles. Let's see the second design aerospace. Global cooperation between IAM policy and IoT policy. As defined by AWS, the identity pool created by the manufacturer is associated with one or more IAM policies. The user or client presenting the credential authenticate can make API requests to any AWS service, such as AWS IoT, S3, and DynamoDB. As allowed by the IAM policy, on receiving the request, the target AWS service queries Cognito based on the credential authenticated to obtain the user's Cognito identity and the associated IAM policy. And based on the service-specific statement in the IAM policy, enforces the policy by determining whether the particular action in the request is allowed. And unlike common AWS service, use IAM policy to authorize the API request. AWS IoT additionally requires an IoT policy with the client. Take IoT publish as an example. One can publish to a specific topic if and only if the IAM policy and the IoT policy both gave him the permission. However, we found that Cognito also supports the authentication method that does not require login. A client can obtain the identity directly as a guest. Similarly, an auth pool binds one or more IAM policies, but unlike the previous case, the client gets an IaaS credential can go directly to interact with AWS IoT without binding an IoT policy. So the authority of the IaaS cred is rather greater and is huge, maybe huge, because it represents the permission of the whole pool. The consequences of the attack may include controlling or monitoring all the vendors' devices. In summary, we noticed that for Outflow, this design is reasonable. The IoT policy by the IaaS pool must be permissive. By the IaaS pool must be permissive to ensure all users can interact with AWS IoT core. But for the IaaS pool, for the IaaS flow, it is not possible to attach an IoT policy to a single identity. So design has to be like below to be for usability. So an IaaS attacker can take credential IaaS without login to do what the IAM policy allows. Note that the IaaS attacker means anyone and no need to be a registered user. Also, either IaaS or IaaS flow may attach an IAM policy of the dangerous IoT API. The IoT API is that AWS IoT opens to developers for managing IoT applications. Attach policy, for example, attach policy or add or delete devices or things. Suppose the Cognito user identity pool is bound to such an IAM policy. Every user has permission to call these dangerous APIs. And in severe cases, attacker can even directly delete all the vendor's data on the AWS IoT. So let's take a look at a demo video of this attack. Note that we did this attack video on our own AWS IoT core account. Now the left is our identity pool and the right is our POC. The row is the new test. and it is attached with a overly permissive IAM policy, and we aim to delete the thing. The name is test thing. And the identity ID will be taken as a parameter as yes. And we get the credential from Cognito, and the thing has been deleted through the attack. There's no thing, no thing. We confirm that we use the same credential from the Cognito. Okay. Now that we have covered two design error spaces, we will move on to the two implementation spaces. The first is the implementation error space 3, dilemma with IoT policy templates. Policy templates are widely adopted as a dynamically compiled policy schema. That is, some variables such as thing name are supported in the policy, and the value of the variable is dynamically populated when the request is received. The thing name is something like device number, and it is unique identifier of a thing. Developers can attach the thing to a certificate or more. However, the semantics of the templates are not enough. See the left figure. If the devices and the users all use the thing name as their policy variable, the allowed MQTT topics are totally different, and they cannot communicate to each other. And if developers want to make the policy secure, they have to implement different static policies for each other, like this. The process is tedious and error-prone, and these policies are not easy to manage. So some vendors implement an overly permissive policy to avoid this problem, such as NetView, whose policy is written like the right. For publish action, they just use a wildcard to let all users share the same policy template. But this policy also means every user can publish to every topic, that is, control every device on the cloud. Let's see a demo of NetView's attack. And the left is the host and the right is the guest. The attacker monitors the traffic of his own traffic to get the AWS Cognito credentials. And he got his credentials. And the host will delete the guest, revoke the guest permission. Now the guest permission has been revoked, and you can confirm it. Okay. The guest permission has been revoked, and the guest can still control the device. Okay. Okay. We take part in another implement aerospace. It's the constraint of IoT policy mutual exclusion. This is a high-level flaws by vendors. That is, the principle of an IoT architecture is not clear now. Some vendors, like Switchboard, design another access control model. See this picture. The Switchboard hub is the control center of all end devices, and the hub can connect to AWS IoT via MQTT protocol. Although the policy of the hub is the hub user is clearly designed and dynamic, multiple users can share the same permission. In other words, share the ownership, and they can even not know each other. Differently, switchboard let device do the access control process, which means the password is saved to end device. In switchboard expectation, when the password is set up, only the user one can control the both one. However, all the control flows must go through the same hub. So that's to say, all the users share the same MQTT topic in the AWS IoT. So the password is not a good design. And attacker can easily monitor the cloud and replay other users' control commands to control the other users' devices. So let's take a look at Switchboard's attack demo. Multiple users can control the same device at the same time. So the host will set a password to the device. And the host can only input the password to control the device. But the attacker can monitor the cloud to get the encrypted control command. Now he cannot control the device by the app, but he can use the script to replay the control command by the host. He can control the device. Attacker can even control the device when the host when he deletes the device. We list the right all the vendors that we found to be in error, and the attack consequences are including control the device, monitor all the device activities or status, fake device messages to users, control the vendor's AWS IoT data. To mitigate the impact and help developers find the IoT policy flows we mentioned, we also present a formal verification tool to check the security of the policies. This is named P-Verify. P-Verify has three basic check capabilities, which are whether an IoT policy soundly includes the permission as expected, whether an IoT policy is less or equally permissive than a reference policy, whether multiple independent policies share permissions. The main insight of the tool is that we translate and encode the IoT policy into SMP formulas, and we leverage the state-of-the-art prover Z3 to solve the formulas, and here is how we do that. Take the policy X as an example. This policy allows the client to subscribe to topic filter start with A/B/. Our basic encoding of the policy is like the fx0. See the right formulas. The action and the resource will be encoded as the SMT symbol. For the first statement, the action equals to IoT subscribe, and the resource matches A/B/point star. Note that the star will be encoded similarly to the point star in regular expression. The A variable is the action and the R is the resource. Similarly, the second statement in the policy X will be encoded to fx1. And since the second statement is a deny statement, so we can encode the policy into SMT format with a conjunction fx0 conjunct not fx1. And similarly, in policy Y, also the hash character is an MQTT wildcard, but we don't encode it now to make it easier. To better illustrate the challenge of p-verifier design, let's review the flow once example. The policy failed to deny topic ABXY because it cannot cover the MQTT semantics. But to design a formal verification tool, we must handle this problem here since we have to follow the semantics of the policy. So we have to design an algorithm or something else to fully semantically support the IoT policy. But not only the IoT policy, also this gap. So the first thing we need to do is to encode the MQTT wildcard characters. Though IoT policy treats them as normal characters, we will encode the plus and hash as wildcard semantics. To encode the MQTT wildcard characters, we must pre-design the character side of MQTT wildcards. The U is the side of UTF-8 symbols. We define the U as the very basic side. The US is the character side of the hash, and just almost the same as U, but we including the side of MQTT reserved characters such as the hash and the plus. And the UP is the character side of the plus. It is the US including the character slash. So the AB hash will be encoded as ABUS star. The star means the closure operation. It's the outstring generated on the character side, and AB plus will be encoded as ABUP star. Then the MQTT wildcards are encoded as the same as the MQTT semantics. However, even with this level of encoding, the policy semantics is not fully covered. Let's see the same example. Policy X does not contain MQTT wildcard, but the topic resource ABXY can still be accessed by the wildcard topic filter, such as AB hash. So the error is due to the wildcard topic that can refer to the same topic. We call these topics IoT synonyms. So given a denied MQTT topic filter, we first confirm that it is relative to one or more allowed statements, and then we must find out the whole set of their IoT synonyms. So we design an alphabet-reduced algorithm which can automate the generation of IoT synonyms from the star wildcard of the IoT policy. Once an IoT synonym is generated and has been accepted by the policy, we confirm that the denied statement can be bypassed or the security property is not satisfiable. We also evaluate p-verifier by comparing it with AWS IoT Defender and by verifying policies of 36 standard and 310 open source IoT projects. And we also summarize the benchmark for IoT policy, including 403 flawed policy and 303 secure policy. Because the Defender does not deal with IoT synonyms and does not take advantage of the security properties, the result of the policies is not as good as our p-verifier. And we also generate a large number of policies from two dimensions, the number of statements and the string length. The results shows that the complexity of p-verifier increases approximately linearly. Okay, now I will make a conclusion of our work. We found new flaws from vendors' practices and brought new understanding of IoT policies security, including two design error space and two implementation space, some realistic security risks and serious consequences. We also present a formal verification tool. This tool can better reason about and fully semantically support the IoT policy. And based on our evaluation, this tool is highly effective and efficient. If you are interested in our work and want to see more details, please see our paper on CCS 2022. Okay, thanks to the audience. Our presentation is over, and you are welcome to ask the questions.
To the microphone and ask questions. No questions from the audience.
Okay. One of the questions I get asked. Okay. One of the questions I get asked the most is how do I know the vendor's policy configuration on the cloud? We did this by reversing the app and simulating the app with our own program. After a lot of testing, we can infer the policy content through the response from the cloud. And in addition, we can also infer the way the cloud organizes the policy by deleting the device, binding the device with another owner user, and so on. Thanks.